Interesting way out of FTA feedback, which is not organized in the topic since they could be organized. The next not selected it, which is the history of the versus the law of information to begin. I can take what I want to do. I don't think it's always specific. So we're lucky if this was strategy or not. And finally, this conference the costs low, both legislation as well as state government costs. And I think over decades it's gotten to a point where for like $2,500 you could actually still conquer. So we're really proud of that achievement. This is the overall layout of the program, which you can go on our website. We have keynotes, panel discussions, things that are here. Just a couple of all the posters are at the back. Throughout the day, so feel free to go have discussions with us. If you like next door, park and sit here because we have talks. And with that, that's a technical program tomorrow. Collaboration work of the highest acceptance rate, which means that it's indicated that collaboration between industry and academia is working. We also have a few items in the technical committee. So we decided to work with the CMT toolkits that maybe many of you are familiar with it, but which was a new file. So we also increased the review of the report was I think it is like 300 and this is what we got as protocol. This had a few reviews for the report. We got the biggest guys that are reviewing the submission. But we introduced this to the guiding for PDF as well. Which was for the reviewer. We also took the review time but introduced the reviewer discussion. With the reviewer discussion, I introduced some kind of workflow for the reviewers who wanted to implement this at how people will react to that. So this is just one more so there's a ton of pictures, but we had 131 reviewers that actually did it for paper, so a bit more than half of the review. Almost all papers. you want to find out what else you was. This is the list of the 13 I've target already. And in terms of review rights, of course we're very thankful for everybody that was there to review us and have identified 11 already provided, especially recognize the what user best best for we also have a best so here we just put the name of the 9 best people who actually and actually the best paper award winner will be announced on Wednesday after the talk. His university came also president of the Signal Processing Society. Welcome to 2022 SLT workshop. I'd like to thank the organizers, all the organizing committee, especially the general chairs, Ahmed Ali and Buvana Ramadran, and the technical chairs for bringing this conference to this part of the world for the first time. I'd like to tell you a little bit about the Signal Processing Society that supports this work. It's the first society of IEEE. It was established in 1948, and this year we're celebrating 75 years of SPS. It has more than 19,000 members around the world, across 120 countries, a network of 1,000 volunteers. It offers a variety of programs and activities for different interests and career stages for students, young researchers, senior researchers. It has a large number of chapters and student branches around the world. So signal processing, what is signal processing? It models and analyzes data representations of physical events to extract information. And the models can be the IEEE Signal Processing Society basically promotes signal processing through high-quality publications, conferences, and educational activities, and leadership opportunities. It advances and disseminates state-of-art information and resources. It educates the signal processing community, and by bringing people together, it catalyzes advances in the area of signal processing. So members of the Signal Processing Society have access to cutting-edge research. They have access to the Signal Processing magazine. This is a award-winning magazine that exposes members to cutting-edge trends in signal processing in a language that is easy to comprehend, so that one can enter the field easily. It provides access to continuing education materials, a large number of networking events for women, young professional students, a new thing that starts this year is a scholarship, so there will be support up to 3 years of somebody to pursue a graduate degree in signal processing. So it's a good opportunity to network, to receive recognition for your work, to amplify signal processing research by becoming a member of the Signal Processing Society. There's a large network of chapters around the world, and you can find at that link the chapter you are closest to. We want to introduce more things to the signal processing activities, society activities. We want to improve the visibility and diversity, outreach to K-12 students, to the public. We want to create curated signal processing educational content. We want to better engage industry. We have started an entrepreneurship forum, and we want to organize challenges and competition. The hackathon that I attended yesterday, which was a very exciting event that brings a lot of people to signal processing. We want to increase our diversity, as I said.
For signal processing advances to reach the real world. So we offer educational course. There are successful entrepreneurs that share their journeys and challenges they met. There's also a forum for pitching ideas. So this started at last ICERS, the largest conference of the Signal Processing Society, and there was a competition, and the first team won $10,000, sponsored by the Signal Processing Society. The sessions can be found at the Signal Processing Society and Processing Society. And so as I said, the Signal Processing Society has celebrated 75 years of this year. It started in 1948. Before that, the sessions Institute of Radio Engineers, and they had the idea to using and so I said all this technology first to use this and they started building companies to support it. This Institute of Radio Engineers, and they had the idea to using and came to so I said all this technology first there are a lot of events this year. They started building companies materials for the to remember this event. You can find more information about all the events by scanning this QR code. Um, if you would like to, if you're not a member and you'd like to become a member, there are two types of memberships. The only difference is that the preferred membership has access to the signal processing digital library. The cost for students is $1 for the essential membership. So if you're a student and you're not a member, it's a good opportunity to become a member and have access to all these benefits. There are special prices for developing countries, and there is a list of eligible countries. You can click on that link and get more information. About speech and language processing, it's the most vibrant field supported by the Signal Processing Society. So the Speech and Language Technical Committee includes the most active and accomplished researchers and technologists in the field. This year, we're still looking at the ICASP submissions, but I wanted to give you an idea of where the various areas stand. And speech and language processing area received the largest number of numbers I can stop here, but it received over 1,500 submissions, by far the largest area, which indicates how vibrant this area is. Okay. So we'd like to further grow this area, and I invite you to give us ideas of what we can do to better support this important area. One last thing, there is an app, the IEEE SPS Events app. If you go to your mobile app store and search IEEE SPS, you can download this app that gives you access to all the information about the signal processing, how to join, how to publish, how to connect, various events. You can find all the information about this workshop and so on. So I hope that you will stay connected, send us your ideas, and I hope that you will enjoy this workshop. Thank you.
So I'd like to thank Athena for having the time and travel all the way to support our conference and supporting SLT for the first time being in the Middle East. Thank you very much for IEEE SPS support for making SLT success in Doha. And with this, we'll go to the next item in our agenda.
All right, well, thank you very much. Let me just check the sound very quickly. Can you send the slides as well to the, can you send the transfer the slides to IEEE SLT meeting because we're controlling the live stream? How do I do that? Just share it with, or send it on an email. Oh, share an email. Do you have it on Google Drive or something? I can put it. Yes.
just see. Okay, I have a better connection. All right. Yeah, there's a noise. Is it because of my alarm? No, it's not. Right. That was just to wake you up. All right. Well, thank you very much for this incredible opportunity, and very happy to be here and to have a chance to tell you a little bit about what we did during the pandemic. And I'm hoping to tell you, about our research on trying to understand the processes that happen in biological and artificial neural networks when we study speech. All right, so this is the very rough diagram of the neural things that are involved. So we have something that we want to communicate, and we send messages to the vocal tract, to the muscles in the vocal tract. We create some vibrations in the air that then they reach the ear of a listener. They produce another set of electrical activity that are then interpreted by the brain, and suddenly they know the message that you wanted to communicate. So this question of how we go from the sound to the meaning, how do we extract meaning from the sound, is something that has been of interest for many, many years. One of the earliest communities that has looked at this and tried to model this is the psycholinguistic community, which they discovered so many different things. For example, the words are understood gradually. They are understood in the context of the lexicon of a person. And of course, in the brain, the biological side of things, we've been trying to model and figure out how different parts of the auditory cortex are connected. What are the like the contribution of different parts. And of course, as this community is very much aware, this has been the target of machine learning to try to automate the process. So I'm hoping to draw some parallels between these different models and these different approaches, and see what we can do to learn from from each of these. So here's a very quick look at the brain and all the stages that are involved in the auditory cortex. So from this time that we hear a sound, the very first thing that happens in the cochlear, we have this frequency decomposition. And from there, it becomes a mystery, but we know that the sound goes through many different stages as it travels up and as it reaches the auditory cortex. And it's really tempting to look at it and, and think of it as a very deep neural network with many different hidden layers. And so, studying the brain, of course, has been challenging for many reasons. One of them has been that it's not very easy to actually reach into the brain and to see the activity of these different areas that are involved. And that's one of the things that has happened in the past couple of decades, that these sort of recordings have become very commonplace in the medical community, in particular for detection and treatment of epilepsy. So when we have patients that have intractable epilepsy, one of the procedures that are now being done is that they go to the operating rooms. They are implanted with electrodes for a period of 1 to 2 weeks, and these patients are in the hospital, and we can go and ask them to participate in our studies by listening to sounds and recording from these brain regions. Right. And so with these sort of recordings, we are now able to record both from the primary areas of the brain, which are shown here with green. That's called the Heschel gyrus. That's where the primary area is. And you can think of it as, if you have the deep neural network, this will be the earlier layers of that network. And we have the areas that are shown in orange, the superior temporal gyrus, and those are the areas that are higher up in that deep neural network. All right, so this is the problem, and these are the tools that we have. And what is it that we are interested in doing, actually? One of the questions that we have in our group is basically just the basic science exploration of speech perception. We want to know how the brain makes sense of speech. We are also interested in emulating these abilities in machines and trying to come up with algorithms and methods that are able to mimic that speech perception, speech enhancement, all sort of things that we see. And of course, a very important area is also to try to figure out with ways that we can help people with disabling hearing loss. And what you see here is a projected number of people with DHL that is about to reach a billion in the next 10 to 20 years. And the method that we have in our group, we believe in an interdisciplinary and integrative approach that using this sort of techniques from neuroscience, from engineering, mix of these things, we can hopefully advance the state of the field, both in the neuroscience side and also hopefully in the engineering and the brain-computer interfaces. All right, so let's look at what we see when we do these sort of recordings. So here, what you see is the cross-section of the brain. And these areas that I showed you, the earlier part of the neural network, the middle parts, and the higher parts are shown here in different colors, HG, PT, STG. And if we ask this person to listen to speech, these are the type of activity that we see in different electrodes. So each of those dots is one electrode, and this person is listening to speech. And so these are the things that we can think of it as the activation of the nodes in the network. And after watching many hours of this sort of video, of course, you may ask yourself, what is this mapping? What are they actually encoding? And if we think of it as this loop that we mentioned, they're going from the sound to meaning. One possible question that you might ask is, what are the units of representation? If you look at one of those nodes that was coming up on and off, what is it that it's responding to in speech? And where and when in the auditory cortex do we see this different information show up? So perhaps the simplest thing that you can do is to ask a person to listen to, let's say, timid sentences. For example, and if you look at one of electrodes that is shown with the red dot, you see that the activity of that node as the person listens to speech goes up and down. And a corpus like timid comes, for example, with phoneme transcription. So you can look at all the instances of a particular phoneme and compare them to all the instances of a different phoneme. And using this sort of different distributions, we might ask, is there any specificity to the responses? And that's indeed what we found a few years ago. Each of these columns is one electrode now in the brain, one part of your auditory cortex. And as you can see, if you look at the average response of those electrodes to different phonemes, we see that the first one responds mostly to the plosive sounds. The second one responds to fricatives. The next two respond to different types of vowels. And the last one is a nasal selective electrode. So every time my sentence has one of these N, M, or ing sounds, this part of the brain seems to go on. Now, these are only 5 electrodes. And we can try to summarize their selectivity using for example, this phoneme selectivity index, and now we can look at it across the entire cortex, and with some clustering of electrodes and phonemes on the y-axis, electrodes on the x-axis, we see that there is definitely a structure here. And to make more sense of it, we can also turn it into a map of phonetic features. And now a lot more structure, becomes obvious. For example, you see all these blue electrodes on the left side are responsive mostly to the plosive sounds. But if you look within those group, you see that a bunch of them respond to the dorsal plosive, some respond to coronal selective plosive, and some to labial. And the same also is true about the vowels. So we have this very nice pattern of selectivity to different types of phonemes in the cortex. And that kind of information seems to become very explicit. All right, so so this is from a few years ago, might be old news now. And let me tell you about some of the more recent work that we've done, which is obviously, when we talk about the phoneme, that's a very early stage of this sort of linguistic feature hierarchy, right? The next thing that happens is that we put phonemes together to form syllables. We put them together to form words, and then that carries different type of semantic meaning. So, what happens to these extra levels, right? Where do we see the evidence of this sort of a more, higher level processing of linguistic information? All right, so to answer that question, we did something similar. We asked people with the electrodes in their head to listen to a lot of natural speech, just basically stories about, audiobook stories. And then we use a representation of these different levels of linguistic features. And we try to use them jointly and ridge regression to try to predict the neural responses from the combination of all these features. And that will allow us to study the contribution of these different features to the response prediction. And of course, we have to do tons of different kind of controls. For example, we go and we replace each one of these with a random, like for example, the phonotactics. Instead of driving them from English, we try to drive them from another language, for example, French or a random language, right? And then that would be a control to see that if phonotactics actually contributes to the signals, to the predictions, how does that compare with just a control? Anyway, after doing all of these sort of controls, what we have is you see the patterns that are shown here. Each of these again is an electrode. For the first one, you see that it doesn't really care about any of these linguistic features. The second one seems to care about phonetic features. The third one, it starts to show also phonotactic and word frequency. And here are three more examples that are in the SDG. So now they are in the higher parts of the auditory cortex. And now we see that there is evidence for more higher level linguistic processing. So if we do something similar again to be able to look at the entire population across the cortex, we see an image like this. That now the y-axis, instead of being phonemes compared to what I showed you before, now there are different levels of linguistics, like phoneme, phonotactics, and then word frequency, lexical information, and semantic. Now, something that you can see is that this phonetic feature seems to be available everywhere, right? So the x-axis are the different electrodes in the brain. Think of it as different parts of your auditory cortex. And it seems like the phonetic features are pretty much present everywhere. We see a pretty clear distinction between the linguistic features that have lexical information versus pre-lexical. So pre and post-lexical information seems to appear in different subgroup of electrodes. And this plot also gives you this idea of that there's a cumulative expression from low to high, right? So things are added to this, but you don't lose the lower level information. But more information seems to be added to that. Here you're looking at the correlation of the rows of that matrix. So basically, we are asking, which linguistic features are represented jointly, and we see a clear correlation between the features that have lexical information. Just emphasize that again. For each of them, we can look at the average distance of those electrodes from the primary part of the auditory cortex. Basically, we're asking, how deep are they in the neural network? And we see that the deeper you are, the more, the sort of a higher level linguistic feature is being represented. Another measure of deepness is the latency of the responses, right? So the neurons that are further up in the auditory pathway are going to see the signal later. And we can use the latency and look at the correlation with this sort of feature encoding. And this also, again, confirms that the electrodes that are higher up seems to be responding to higher level information. We can use also using a dimensionality reduction of these encoded features. And now these dots each dot is an electrode and it's colored by where it is in the auditory cortex. Blue ones are in HG, more superficial layers, and the red ones are in SDG. So they're the higher parts of the cortex. And we see a very nice and clear separation of these different colors. Which again tells us that there's an anatomical distribution of these features, and it's also shown here by the fraction of sites in different areas that respond to these features. So basically what we find is that there is an explicit and distributed neural encoding of all these different levels of linguistic that we look at. And the distribution of the pre and post lexical features seems to be very nicely separated. And as you go from the primary parts of the auditory cortex to the higher parts of the auditory cortex, we also see that the tuning changes from low-level linguistic features to higher-level linguistic features. We can also look at the question of when these features show up by looking at their encoding time. And as you go from acoustic to phonetic, phonotactic, word frequency, and lexical and semantic information, we see that these features tend to show up later and later in the brain, as it is also quantified with this plot. So, we set up to answer this question of what features are encoded, where they are encoded, and when. And, we have now an answer for those. We know what features are there. We know that, how they are anatomically distributed across the cortex and when they show up. One question that we haven't addressed is that how are these features extracted from the sound? Right? So we just confirmed that they are there, but how? And that is a very difficult question to answer, especially because we don't really have a very good model, a computational model of human speech recognition. And, of course, the advances that has come from the engineering community, and, it's funny because we tend to always ask for the opposite, right? Like we all want to know if we learn something about how the brain does it, maybe we can make better algorithms. But it's usually, sometimes it's just the opposite. Advances in the ASR is actually leading us to learn more and more about HSR. So this question that we were interested in is to take an end-to-end speech recognition system and basically see, are these features that we see in the brain, are they also extracted in this sort of end-to-end systems? And if we try to relate the two, if we try to take the levels of these sort of end-to-end ASR and relate them to the layers of the cortex, do we see any similarity between the two? Between the representation that they use, between the units that they extract? So ASR, as you all know, used to be this sort of an explicit separation of levels, right? We used to have feature extraction, acoustic model, model of a lexicon, and language model on top of all of it. And in recent years, it has all become into just one thing, right? We no longer ask it to explicitly extract any of these sort of levels, and everything is implicit. So one of the candidates that we use for this is an RNNT, RNN transducer. It has a state-of-the-art performance, and it's also just a nice model because it's neurally plausible compared to more for example a transformer that you have to make some difficult assumptions. For example, having access to the past with no constraint. So anyway, in collaboration with some of our colleagues at IBM, we use basically an off-the-shelf RNN transducer model. As many of you know, it has a transcription layer. In this case, 6 of them, and then it has a prediction unit, which basically takes each of the outputs and feeds them back in a feedback layer to the prediction network. So if we do something very similar to what we did with the brain, okay, so we just basically take all of these descriptions of, so we run speech through this model, and then we express our speech using these different levels of linguistic hierarchy, and we ask, if we try to predict those in different layers of the network, what sort of progression do we see? And we see something that is probably makes sense, and it's similar to what we see in the brain, which is that if you go from more acoustic level representations like pitch, spectral centroid, to more like pre-lexical, like phoneme surprisal or phoneme probability, to more lexical and semantic, we see that they are extracted later and later in the network from T1 to T6. This was not the case in just a randomly initialized unit model. And also, if we train it on something like French, a different language, we also don't see this sort of progression. So these are just controls to make sure that, this is not a property of this structure. Now, if we take this RNNT and different layers of this network and try to predict the brain signals, what we see is a plot like this, which is on the x-axis, you have the layers of the RNNT, and then the y-axis, you have the layers of the cortex, roughly ordered from low to high. And, you see also this nice property that seems that the deeper you go in your network, the deeper areas of the brain you are able to predict. And on the other hand, if we look at the layers of the network, of the biological networks, right? So if we have the group of electrodes, and if we, for example, try to separate them by how far they are from the primary auditory cortex as a measure of how deep they are in the biological network, we see also that there is a nice separation of pre-lexical and post-lexical. So when you go deep in the brain, that's the only time that you can actually extract this sort of lexical and semantic information with a high accuracy. And that's also shown here in the brain. It's a little, complicated to make sense, but those plots that are on the top, I guess, are more easily interpretable. All right, so this is a nice, result, but it provides a, relationship between artificial and biological neural networks. And now to go deeper into this question, we also looked at the time. Because, if you think about going from phonetic to lexical to semantic, you're basically integrating over longer and longer time durations. What you see here is the density of the phonemes, syllables, and words. And obviously, as you all know, the higher you go into this sort of thing, like if you go to a word level representation, you need to integrate over longer time durations. And something that also is very important to keep in mind is that there is a lot of variability in natural speech. For example, this graph on the left shows the distribution of the duration of the word before. And in some cases you have 200 milliseconds, and some cases you have 800. So it's a huge variability. That's also shown in the graph on the right, which shows the overall variability of speech. So all of that has to be dealt with, either in a biological neural network or in the artificial neural network. So how do we study this? How do we get a network, either the brain or an ASR? And we ask, how long does it integrate, right? What is the integration window that this network uses? So we came up with this paradigm, which we call temporal context invariant paradigm, which is if you consider a sound, for example, in this case, a blue one, and if you embed that sound into a context, okay, so you have a sound that precedes it and one that comes after. You can create many different contexts, right? You can change the sound that came before, many, many times with different types of sound. Now, if you think about it, if you're looking at the response to the blue sound, at the beginning of that, of course, the response is going to be very different because it depends on what came before, which is random. But if the duration of this blue sound is long enough, towards the end, hopefully the response becomes similar in both contexts. But basically, if the segment duration is greater than the integration window, then the response to the blue sound towards the end of it is going to be the same in both contexts, right? But if the integration window is larger than the segment duration, then you never get the same response in these two different contexts. So by changing the length of this segment, we are able to distinguish, to identify the integration window without using any model. Which is really great because if you're working with very nonlinear systems, it's very hard to make sure that you have the right model. All right, so the question that we ask, can we take these sounds to people in many different contexts, and we record it from the brain, and then we just look at the correlation before the sound and when the sound is towards the end of the sound. And hopefully the correlation at the beginning will be close to 0, and towards the end, if you have long enough segments, it should reach 1. All right, so what do we see? So this is what we see in the brain. And you see the integration window with different colors. And it's very nicely organized. So as you go from the earlier part of the auditory cortex, the primary like auditory cortex to secondary, um, basically, again, if you think of it as a deep network, if you're going from the superficial layers of the brain to deeper layers, you see that it's integrating over longer and longer durations. And interestingly, we also didn't see any difference between the left and right hemispheres. And if you look at how, this context, one thing that came for free is that we are using many different sound categories. So we can also look at the distinction between these categories. And if you're looking at the areas, those blue dots, the areas that have a very short integration window, they don't seem to really distinguish between different sound categories. But as we get to the longer and longer integration windows, the higher parts of the brain, then we see that these categories also become very separated. All right, so again, we try to do something similar. So instead of now playing these sounds to a human, we play them to a machine. Okay, and here we are using the deep speech 2 from Baidu. And we play the same sounds to this to that, and by playing with the segment duration, we can look at the integration window. We can ask, any node. If you take any node in this network, you can measure exactly how long is the temporal integration of that node by basically looking at, when does the response to that becomes the same across different contexts. So here's the result of that. If you're looking at so what you see here is the different layers of these network, deep speech 2. And if they are randomly initialized at the beginning, you see that the integration window is pretty much the same across the network. But as the network learns to recognize the speech, you see that it becomes longer, deeper layers become, have higher and higher temporal integration window, which is an intuitive finding, but it's quite interesting. And the nice thing now to look at is the variability. Okay, so this integration windows, is it a fixed thing in the network? Like for example, if you look at the node and if you measure the integration window, and half a second, basically it's looking at past half a second of the signal. But we know that the speech is very variable, right? So if I'm speaking fast or slow, that contains different number of phonemes. So how do we deal with that? And that's actually quite easy to test. All we have to do is to time compress or time stretch our signal and play it again to the network and measure the temporal integration again, right? So if the integration window is time-based, then it doesn't matter whether you time compress or time stretch the signal. But if it's not, and if it's feature-based, then the faster the speech is, the shorter the integration window should become. All right, so here's what you see. Basically, the temporal integration measured with natural speech versus with time compressed speech on the y-axis. And in the earlier layers, it's pretty much on the unity line, on the black line, right? Which means that it doesn't matter what you do. It just is interested in half a second of the speech signal. The red line shows you the feature base. So if it actually adapts and becomes changes the integration window based on the speech of the speech, speed of the speech, you expect to see something on the red line. So as we go deeper into the network, you see that it shifts gradually from the black line all the way to the red line. And here it shows the summary. So it's very interesting because as you go deeper into the network, the representation changes from a time base to a feature base, which is also shown here. So basically, low to high layer changes from time base to feature base, and integration window at later parts of the network are very adaptive, but not in the earlier part of the network, right? They're fixed, but they're very adaptive towards the end. All right, so I just want to basically very briefly also mention some of the work that we did on the music, because music is also similar to speech, right? It has short and temporal context dependencies. which is, part of the things that the composers play with to, for example, to surprise you or to, to create tension, release the tension. And, you can ask basically the same kind of question, like, is this sort of temporal dependencies encoded in the brain and as we listen to speech? And one extra thing that we have is that musical training, if you take musicals, professional musicians, you might be wondering, do they look at more context compared to somebody who doesn't have musical training? So again, to study that, we need a good model of the context. And in this case, again, we use a transformer model. So it's an off-the-shelf music transformer that can generate very enjoyable music. We pass, Bach pieces through this network. We reduce it using non-negative matrix factorization, and then we use it to predict the neural responses. So we basically play the same Bach pieces to people and to a transformer, and we're trying to see if there's a relationship between these two. So first, if we just look at the network itself, and to see what happens as you go through the network, we see that, in the earlier layers, for example, if you look at the note duration, the representation is completely mixed, right? All the notes with all different durations are mixed together. But, when you get to the layer 5, maybe, then you see a nice separation between them. If we classifying pieces from the notes in the music, we see, again, as you get to the deeper layers, it does better. You don't have to go too deep to be able to do that. More, contextual information. So example, looking at different pieces, Bach melody number 1 versus 2, that only shows up when you go very deep in the network. And if you look at, for example, the prediction of the next note from the current note, we see that the information also, at the deeper you go, it becomes better and better. So this is just an investigation of seeing, is context actually being used in this sort of a transformer, right? If you go deeper and deeper in the network, are you actually using more and more context? And that seems to be the case. Now, let's try to relate this, right? So now we take the activations of this network and we try to predict the neural responses. And this is the EEG case. So this is, we put cap on people and we ask them to listen to music. I think we had 20 musicians and 20 non-musicians. And when you do that, and you look at the correlation in the accuracy of the correlation between actual and predicted responses across layers, we see a panel, plots like this. And in this case, they're clustered into 2 different clusters, which surprisingly are perfectly anatomically separated. So all the blue ones are in the front of the cortex, all the red ones are in the back. But this was a functional clustering. We didn't look at the location of the electrons. We just look at the functional properties, and it happened to be perfectly organized. And this blue cluster is particularly interesting because at the very end of the network, it shows a jump. Now, what's interesting is when you look at this between musician and non-musicians. And the first thing that we see is that the musicians have a much more predictable response from the layers of this network. So the x-axis is, again, the layers of the network. And if we look at the difference between these two, we see that the deeper we go within the network, the larger the difference between musician and non-musician also becomes. And this rise that I mentioned that towards the end, you only see that for the musician and not in the non-musician group. So yeah, it seems like the deeper we are in the network, the more context that is being integrated, the better the neural prediction accuracy, and music expertise seems to play a role in how much context people use. All right, so these are all attempts to try to figure out the connection between these sort of artificial and biological neural networks, what representations they use, how do they deal with time, what kind of units they try to extract. Let me switch gears a little bit and tell you also about the work that we do on the third part of that, maps that I had, which is on brain-computer interfaces. So you probably know about the BCI. It's basically uses some form of recording of the neural activity in the brain and uses that to either replace, restore, enhance, or supplement a function for a user. It could also be the other way around. It could be used to treat, enhance, or alter a function by writing something into the brain. And this is the field that, like all other fields, has seen tremendous progress in this past years. And I picked a few examples to show you here. One is from the BrainGate 2 project, that people who are paralyzed are able to, to use the chat to browse the web, watch videos by just thinking about the action that they want to do. A lot of work is being done on speech, which to try to decode speech directly from the motor cortex. Like, for example, a person who is unable to talk, they can think about what they want to say, and they can try to extract that. And this is also another recent work which has tried to decode handwriting. So the person in this case is paralyzed, but they are just imagining writing characters. And that can now be coded at 90 characters per minute, which is really fast if you think about it. Like, normal typing on a phone is about 180 characters per minute. So this is like halfway there already. And the area that we are interested in is enhancing speech perception, particularly in noise. Because as you know, for people who have hearing loss, this is a huge challenge. And this is where we live. So this is the map of noise in the United States. And it's becoming more and more noisy. And something that always puzzled me is the correlation between this map and the map of the drought in the US. And there's this perfect negative correlation, which makes you wonder if noise has something to do with rain. Anyway, so going back to the noise, so one of the things that problems that we are interested in is this sort of listening in multi-talker scenes. And we had this scientific discovery a few years ago, which is if you look at the speech that's represented in the brain, and if there are more than one person talking, you only see the person that is the focus of the attention. So these two plots, for example, are reconstructed spectrograms. So somebody was listening to speech, we recorded from their brain, and then we reconstructed the spectrogram from their brain. When they listen to a blue speaker, listen to a red speaker. Now, if they listen to the mix of these two and pay attention to blue or red, we see these following spectrograms. And if we overlap them, you see that there's a very nice match between them. So the speech that's coming out of the brain only looks like the person that you're attending to. And this is a basic science finding, but it also enabled this idea of having a brain control hearable devices. And what that means is that imagine that you can be in a party. You might be, there might be simultaneous conversations happening there. Maybe you want to on one, maybe you want to switch your attention to the other one. And, this is easy for us to do, but for, people who have hearing disabilities, hearing loss, for example, that this is not a very easy task. So the question here is, if we are able to detect who the person wants to listen to, is it possible to use that information to enhance that conversation? And this is something that you can't do with signal processing alone, right? Because you don't know which conversation is noise and which conversation is target. So this is what a system like that would look like. You have a method, some kind of a speech separation. And this is actually the reason that we got interested in speech separation and this sort of a deep attractor network, the TASNet, that systems that you might have heard of. Were basically motivated by this need that we needed to have a method of separating talkers. And when we do that, then we can compare them individually to the brain, and the one that is most similar to the brain, we can amplify that. And we've done some work on that. For example, the one that I mentioned at the bottom. So this was published a few years ago. Our most recent attempt on this problem is to try to go towards more realistic scenarios. For example, when you have not simultaneous talkers, right? So we always assume that there is talker A, talker B, talker C, and which one is the attended. But in reality, we always have conversations, right? So in this case, you're not interested in one talker or the other talker, but conversation one versus conversation two. And that's different because, talkers can take turn, they can move into space. If you want to do it correctly, you need to maintain their location in space for the there will be noise, there will be reverberation. And so we have a new paradigm now that, we have a person listening to a room, we have two conversations. These conversations are moving in space, there's noise, there's reverberation. And basically, we have a binaural speech separation that is also able to preserve spatial cues. And it's controlled with neural signals, right? So it's a brain-controlled speech separation. And here is a demo of how well a system that would work. So you have a box, which we call auditory attention decoder. It has basically two inputs: the sound in the environment and the brain signal. And the output of that is the modified audio, which hopefully is easier to listen to. So here is in this demo, you're going to hear two talkers. First, the male speaker is the focus of the attention, and then the listener switches to the female talker. And we turn on the All right, so hopefully it was easier for you to listen to the conversation with the amplified audio. And I think that the sound quality in this room is not great, which is good for this demo. So you can see, how you can see the difference more easily. All right, so of course, we tested it also objectively. We confirmed that when we do this, people are able to track the talker better. The speech becomes more intelligible for them, and it's also more easy to listen to. So this sort of technology doesn't only have application for people with hearing loss, but I think every one of us can benefit from it. If you go to a noisy place or a noisy bar, it's really tiring to try to listen to people, right? So it can reduce listening effort and cognitive fatigue. All right, so to summarize, and I think I'm compensating for the time, so which is good. So you get the coffee on time. Yeah, so we show, basically we see a converging representation and computation of linguistic information in both biological and artificial neural network. We see this hierarchical representation and joint and distributed representation of time scales, linguistic units. Hopefully I just gave you a flavor of the sort of speech-brain computer interfaces that we and others are working on to restore and improve speech communication. And I should really acknowledge the people who actually did the work, especially Sam, Manuel, Vishal, Yinghao, and Kong. Yinghao has a paper also here on TTS. I was very happy to see he was one of the finalists. So make sure to check his post there. And our collaborators, Samuel Thomas, George Sean, and Brian Kingsbury at IBM, and our funding sources. And thank you very much for listening. Maybe I will start that. So I'm actually very interested in your the area of financing, mostly different than startup activities. And my question is for the recently people are using the self power planning here, not only try to say any other linguistic part, but the self power information about linguistic information, speak information, emotional information, particularly information. So do you have some kind of analysis of direction or academic speech and everything about model? And what the kind of not only linguistic information, but Yeah, I think that's a very good question, and definitely, and there is the only reason we haven't done that is to try to start simple. But obviously, of course, a person, we know that the person does more than just trying to transcribe speech, right? That they are able to recognize the talker, recognize the emotional significance, detect the prosody, the tone, uh, all of that information. And that's definitely something. So we've studied that in the brain, like we play, speech with different emotional significance to people, and you see that the brain encodes that in the same areas that encode the linguistic information. And definitely for a more complete picture, we have to move in that direction and have models that are not just looking at the linguistic information, but also include paralinguistic. So yeah, I mean, if you have ideas on what kind of models would be more appropriate for this, then that definitely is. Do you have an example of the larger unit? Like, are you still having? Yeah, yeah. So I mean, yeah, we started with the um, but pretty quickly moved on to this sort of a larger representation. So in this, for example, the plot that I showed here, if you're looking at the top parts of that features that we use for the prediction of the responses, that's past those are using board level information. And we have also some work that uses more context level information, which I didn't show today. But yeah, but definitely phonic was the starting point, and we've passed that, and we're looking at other. Yeah, but it's also interesting to see that, as you said, like for example, the new models, they don't have to. Like if you train an end-to-end ASR, you don't ask it to represent phonemes, right? If it does, perhaps it did it because it was useful to it. And that was interesting to see that, if we take an RNNT that was trained end-to-end, still you see the representation of this sort of phonetic information at the earlier part. So it seems like that information is still useful, at least implicitly, is used both in the brain and in the artificial XR. Oh, okay, yeah. Are you referring to this plot? Yeah, yeah. So of course, here we are testing it on English. Right? So we are testing on, for example, if you're looking at, I don't know, phonotactic information in English, in a model that is trained on English, you see that, oh, that information, it seems to appear in later layers. But if you're looking at English information in the French model, yeah, it doesn't show. So it was basically just a control, because, like for the very acoustic information, like for example, spectral centroid, that doesn't seem to really depend on training. You don't have to train it on English to see that, because it shows up in the random and in the French model. So this was a test to see that, to make sure that these sort of information actually is being extracted because of the training of the network. Yeah, thanks for the question. Yeah, of course, this is the motivation that I started working on this sort of when I was a graduate student, long time ago, when XR was not working, and the brain was doing so well. So that has always been the motivation. Um, and it's interesting to see that these two are converging, right? Like we are now using neural networks, which is more brain-like than, for example, I don't know, some of the older models that were used. So you see this convergence, but how much of it happened because we learned more about the brain? The honest answer is that I don't know. It seems like through the engineering, we are basically optimizing and stumbling upon the same kind of principles that also exist in the brain. But it's also quite of a challenging task because when you're dealing with the brain, you have an extremely deep, complex neural network, billions of nodes, and you can't record from these nodes, right? You see the aggregate of the response from many layers combined together. And it's a hard task because even if you have a network, an artificial neural network, and you try to analyze it to figure out what it does, we don't really have a good answer for that. So with the brain, it's just more complicated. So I think that, yeah, this it would be very nice if we can learn something from the brain that is, as you said, actionable and can lead to better XR. And I don't know. I think the honest answer is that I think most of the contribution has been the other way around. Like the better models we might have, the more we learn about how this can be solved, the more also we learn about the brain. I just end with one comment that is one of the works that we did that I didn't have time to include today was to use neural networks to try to figure out what are the receptive fields, what kind of computation is performed in the brain. And there we found some really interesting computations. Like, for example, parts of the brain that hold on to a feature, respond to it for a while. They have these sort of complex adaptive mechanisms that, especially when you go to a noisy situation, they quickly change the receptive field to filter out the noise and to keep the speech. But something that at that level that can actually help this community to advance, that has always been the motivation, but I don't know what I can offer. That's, I'm sorry, what kind of structure are you talking about of the brain? What layers? Oh, yeah. It comes with some kind of a pre-wiring. It's not completely randomly initialized. Um, um, yeah, it's a hard question. It's a question that I wish I could have a good answer to. And I think so. It's good to keep in mind that that field also, like we are, the neuroimaging techniques that are coming available now, and the possibilities of to record from tens of thousands of neurons simultaneously, not in humans but in animal models. right? These connectomics projects that, for example, try to figure out all the connection between all the nodes in the brain. So these sort of things, I think they are providing more and more data, and that field also has a challenge now that they have too much data and not enough ways, good ways to make sense of it. But I think at the course level, anatomically, we knew for a very long time that there are these different layers or different stops, right? But there is a problem of resolution. Because if you actually want to get to the point that you can say something about, okay, how can I make a model of this? We need to have a much higher resolution. These electrodes that I showed you, which is very advanced compared to like EEG that you put on the scalp, right? So this now you put it inside the brain. But still, each of these electrodes is relatively large, and they probably show the activity of tens of, or maybe hundreds of thousands of neurons combined. So I think, to get to the level that we can use that as an actionable information, or as you said, to learn something about, for example, the structure, we need higher resolution, and that field is getting there. So hopefully in the near future, we will have enough data and then solve the challenge of how to make sense of the data to learn something that is like more than just, yeah, I mean, for me, just the scientific challenge of it, just to figure out how the brain works. How does it fall apart? For example, in different types of speech and communication disorder. That is a very interesting question. And what we learned from ASR is helping in that a lot. But yeah, hopefully as we learn more about the brain, there will be also something that we can bring back to this field.
Speaking of that, did you say the brain's process switching? We hear a lot of is there some way to it's like
So like how we switch language, how do we yeah, no, that's a very interesting property, and we don't know much about it. One of the things is that the patient. So when we talk about this sort of intracranial recordings that gives you access to very relatively high resolution data, the thing is that we have to work with the population that is coming through the hospitals, right? So for something like if you want to, for example, study. Like, for example, the study with the music, when we wanted to look at the brain of the musician versus non-musician, is extremely hard to do with that kind of data because you don't have any control over your patient population. Oh. Well, we need the brains, so yeah. But that's also a difficulty when we have these sort of patients. We have multilingual patients that you can design a task to study, for example, code switching. Yeah, but there are definitely fascinating things happens in the brain when you learn second languages. These patients that they come through, eventually they lose a part of the brain, right? So after the patient, after the surgeons localize the seizure location, or in cases that they have a brain tumor, then they go and they take out that part of the brain. And in many of these cases, especially in bilingual people, you see that one language is impaired, the other one is intact. And you see all kinds of different deficits. Like people get an accent, their accent, for example, changes after they have this sort of, so there is definitely overlapping, but also separate representation of different languages in the brain and how they are used in code switching. That's a fascinating question. Hopefully we'll have an answer one day. Yeah.